Thanks so much. Thanks so much for coming, and we're very happy to have Arthur Lipstein here, who's going to tell us about cosmological scattering.
Hey, thank you very much, and thanks for the organizers for giving me the opportunity to speak here today. I'm going to talk about some recent work I did in collaboration with America Gomez, Renan Lipinski-Usinskas, and my students Connor Armstrong and GHMA on what are called the cosmological scattering equations.
You should be very careful with this thing not to hit the screen.
Okay.
It's the expensive one.
Okay, I'll keep it with you. I'm not able to.
You have to press share and then
Stop share?
Yes, stop share. I will remove the full screen, share, and then go to full screen.
Oh, no. Okay, let's try it again. Okay, good. Thank you. Yeah. All right, so before I get into the details of this, let me just give some kind of basic overview and some historical context. So a lot of this work is inspired by work on scattering amplitudes in flat space over the past few decades, and obviously this audience, I'm sure, is familiar with the concept of a scattering amplitude, but let me just say that they are the basic observables that are measured at particle colliders and that allow us to compare theoretical predictions with experiment, and so they're of tremendous practical importance. But on the other hand, they also have a rich mathematical structure, which is interesting in its own right. For example, all the way back in the 1980s, thank you, Park and Taylor just discovered, I think, experimentally, if you like, or using a supercomputer, that a certain class of amplitudes known as MHV amplitudes that describe scattering of gluons, two with minus helicity and the rest with positive helicity, can be described using this very compact formula for any number of legs. Now, the details of this notation aren't really going to be relevant for this talk. The main thing to get from this is that that's something very hard to see using standard Feynman diagram techniques, right? Because the number of Feynman diagrams explodes as the number of legs goes to infinity. They go roughly like n factorial, and yet in the end of the day, somehow they add up to a very concise expression. And so what this is hinting is that there's some deeper structure in quantum field theory, which is being missed by standard textbook techniques. And you may ask, is there a way to reformulate quantum field theory that makes this structure manifest? And at least in the context of n equals 4 super Yang-Mills at tree level, the answer to this question was answered by Berkovitz and Witten, building on the very important insights of Nair. And the answer to this is that this structure is basically a consequence of the fact that n equals 4 can be reformulated as a twistor string theory. Okay, I won't go into the details of that, but at least at the level of words, that's roughly speaking where this structure is coming from. And this led to an explosion of progress in the study of scattering amplitudes. It led to recursion relations, new geometrical ways of describing amplitudes, and many powerful new techniques. But for a long time, it's still very unclear how this twistor string theory description extends beyond this very, very special theory known as n equals 4 super Yang-Mills. And in particular, how do you use it to describe more generic theories, or ideally, the standard model, for example? And this is an open question for quite a long time. Oh, going in the wrong direction.
And then we hit the left arrow.
Thank you. Okay, very good. Right, and for a long time, this was an open question until around 2013, when Cachazo, Yuan understood how to generalize it to a very, very broad class of quantum field theories. I would say probably any quantum field theory involving massless particles. So in particular, Yang-Mills theory, non-supersymmetric in general dimensions, Einstein gravity in general dimensions, and a whole other wide range of QFTs that I'll describe shortly. And the backbone of their formula is this very deceptively simple looking set of equations known as the scattering equations, which were actually first discovered in the early days of string theory by Fairley and Roberts, and then later rediscovered by Gross and Mende by considering the tensionless limit of string theory. And I think at the time, no one really appreciated what their significance was until CHY came around. And in a nutshell, what these equations are the following. So at tree level, at n points, I would put n punctures on the Riemann sphere, and I would assign a complex number to each of these. So I do a stereographic projection to the complex plane. And so the location of the puncture for particle A is, I'll denote as sigma A. And then sigma AB is just equal to sigma A minus sigma B. And then Ka is the momentum of the kth particle, which we take to be null. So these are massless particles. And then all you have to do is solve these equations. And very superficially, this looks like just a problem in two-dimensional electrostatics, right? So this is basically equivalent to finding static configurations of point charges on a sphere. But quite amazingly, this seems to underlie the scattering amplitudes of, as I said, any massless quantum field theory. Not only at tree level, but also at loop level. At higher loops, as we'll see shortly, you just have to add more punctures onto the sphere. And so what they found was this remarkably beautiful universal structure where any massless, the scattering amplitudes of any massless scattering amplitude at tree level can be written as an integral over n-3 world sheet coordinates. So I choose 3 of them and I fix them in the usual way that you would do in perturbative string theory, and then I integrate over the remaining n-3. And they are supported on solutions of the scattering equations. And one way to phrase that is to think of this as a contour integral and write these scattering equations as poles of the contour integral, and then the contour basically encircles the locations of these poles. And so this appears for any scattering amplitude of massless particles. And then the theory dependent part depends on this integrand, okay? So if I describe Yang-Mills, it'll be one integrand. If I describe gravity, it's another integrand. And the integrands themselves can also be expressed in terms of a very simple set of building blocks, as we'll see shortly. So there's clearly something very beautiful about this and surprising in a way. To be honest, I still don't know what the significance of it is, why perturbative Q of T really wants to have this form, but this seems to be the form that it wants. And it really makes a lot of properties of amplitudes that were previously mysterious much more manifest.
Sorry, can you remind us this for loops as well, or just two levels?
Yeah. So it's going to go. It's for loops as well. I'm going to say a little bit more about that in a second. Okay, good. Right. So after these were developed, there were, I think, a lot of interesting applications and new techniques for computing things at tree level as well as loop level. And for example, it led to new representations of loop amplitudes, basically in terms of tree level amplitudes, in the sense that, for example, at one loop, at one loop 4 point, you can obtain from this picture from adding 2 additional auxiliary punctures, if you like, in addition to the 4 external ones. And then you think of there being sort of a thin tube connecting them. So you think of it as coming from the degeneration of a torus. And what this thin tube basically does for you is it tells you to take the forward limit. In other words, it tells you to take the limit where the momenta of these 2 auxiliary punctures are equal and opposite, and then you integrate over that momentum, and that's what gives you the loop integral. And then to go to higher loops, for every time you go 1 loop higher, you just add an additional pair of punctures. Okay, and so it led to this interesting new representation and new techniques for computing loop amplitudes. But for me, the thing that really blew me away about the CHY formula is that they revealed just this very surprising new web of relationships between many different QFTs that I don't think anyone really expected beforehand. Except, so it was not known for a long time before that in some rough sense, Einstein gravity is a square of Yang-Mills. I'll try to make that more precise later. And that actually becomes manifest in this language, at least at tree level. And what else it does is it tells you that it sort of extends the scope of this what's called the double copy relation to many other theories. For example, there's the nonlinear sigma model, which describes pions. When you square it, it turns out to describe something called the special Galilean theories. And there are many, many other examples. And I think prior to the CHY formula, no one ever expected things like this, because certainly if you look at the Lagrangian for these theories, they look completely unrelated. But from the point of view of the CHY formula, on the previous slide, these relationships correspond to very, very simple operations at the level of the integrand. So for me, I think this is the main power of this approach. It gives you this theoretical insight that I think was very hard to see any other way. Okay, so the questions I want to address in this talk are basically, can this progress be extended to cosmological observables? And in my opinion, at least, this is an important question, because whereas scattering amplitudes describe physics at their shortest scales, cosmology describes physics at its largest scales. And if there's a way to import all of these ideas and techniques to cosmology, I think that would lead to many powerful new techniques and theoretical insights. But it's not just a one-way street, because if you want to describe cosmology, you necessarily have to work in curved background. And so that would in turn give us a deeper understanding of these properties that were discovered in flat space. So in particular, one important question you would ask are the scatter equations and double copy fundamental? Or are they in some sense just an artifact of working in flat space? And I should mention that many other tools have recently been developed to describe cosmological observables, which have been inspired by amplitude techniques. For example, Mellon-Barnes techniques, techniques based on factorization and unitarity methods. And by now, this is a very, very active subject, but I won't really have time to discuss these other approaches. Okay, so now let me be a little bit more precise about what I mean by cosmological observable. So in this talk, I'm going to be working in the framework of inflation, which postulated that the early universe was approximately described by a four-dimensional de Sitter space. And then things that people measure, like the cosmic microwave background, can roughly speaking be derived from correlation functions at the future boundary. So this is the metric of de Sitter space, where eta is the conformal time, which goes from -infinity to 0, and then the future boundary is located at eta equals to 0. And this index I runs over the boundary directions, which we set to go from 1 to 3 in practice, because we live in 4 dimensions. And then the idea, roughly speaking, is that you compute some kind of correlation function, like a Witten diagram that ends on the future boundary, and then use these correlation functions in turn tell you how to compute observable quantities like the CMB.
So the future boundary is actually null past.
Sorry?
Future boundary is actually null past.
Null past.
In our past. I mean, it's at the end of the.
Oh yes, that's right. Yes, and then there's FRW and so on after this, indeed. Yeah. So in fact, we don't actually go all the way up to 8 equals 0. At some point, there's a transition. Indeed. Okay. So let me be a little bit more precise about how to compute these quantities. So in practice, what one computes are what are called in correlators, and they can be computed from something called the wave function of the universe. This terminology makes me cringe a little bit, to be honest, but it seems to be the standard one used.
Just call it the wave function of the universe.
I'll call it a cosmological wave function.
Yeah.
I'm not going to use the word universe too much. So anyway, there's this object which we'll refer to as the cosmological wave function. And the idea here is, just for simplicity, we're just going to assume that we have scalars in the bulk. And this object here, phi, it corresponds to the value of the scalar at the future boundary. Okay? And what you do is you have this wave function, which is a functional of phi, and you square it. That gives you a probability. And then you do this integral over the boundary values of the scalar field phi. Okay? And then typically in cosmology, people also Fourier transform it to momentum space. So these k's you think of as vectors, momenta in the boundary, in the future boundary. And perturbatively, this wave function can be expanded in the series. And then it turns out that every coefficient in the series called psi n, obeys conformal ward identities that are basically inherited from the isometries of de Sitter. And as a result, formally, you can treat them as correlation functions of a CFT in the future boundary. I'm not going to make any statement about the existence of such a CFT, because that is still unclear. But at least formally, you can treat these things like CFT correlators. And moreover, you can compute them from Witten diagrams that end on the boundary and can be obtained basically from ADS Witten diagrams by an analytic continuation. Okay, so roughly speaking, the way I think about this is that the wave function coefficients are like the amplitudes, and the in correlators are like a cross section in the sense that you square the amplitude and then you integrate over it. And so it's these wave function coefficients psi n that I'm going to be focusing on in this talk.
Sorry, you're integrating over phi in the bulk, or the bulk fields.
Well, yes, you have a bulk path integral, but this integral is actually over the boundary values of phi. So phi here denotes a boundary value. So whereas in ADS, it's very different than in ADS holography. In DS, you actually have to integrate over the boundary values of the fields. And this also includes the graviton in principle. So you also have to, in principle, integrate over the value of the metric at the boundary, which is why de Sitter holography is a much, if that's a sensible concept, is a much more subtle thing to define. But for simplicity, or at least perturbatively, if you like, I'm going to work with a fixed background metric and then just integrate over the boundary values of the scalar field.
Okay, thanks.
Perfect. Good. So as I said, in practice, we Fourier transform these boundary correlators to momentum space, and there are a number of reasons for doing it. First of all, this is the standard language that cosmologists use, and so it's good to use the language that can in principle be connected with experiments and that this community would be familiar with. But it also turns out to have practical value because working in momentum space is very useful for studying soft limits and factorization, like for example, the flat space limit and so on, as we'll see later. And so it's good to keep in mind, though, that of course, momentum is only conserved along the boundary, but the energy isn't conserved because of the time dependence of the metric. Okay? And so working in momentum space, we can then define these conformal generators in the boundary. So again, this index I runs from 1 to 3 in practice, because we're working with 3D Euclidean boundary. And then this P is the momentum, is the generator of translations. D is the generator of dilatations. Ki is the conformal boost, and Mij are the rotations. And you'll notice the appearance of D here, that's the boundary dimension, which we set equal to 3 in practice. And delta here is a scaling dimension that you associate with the operators living in the boundary. And that's related to the mass of the bulk scalar in the standard way. Okay. Good. And then perturbatively, you can compute these Witten diagrams using the following Feynman rules. So it's a very, very useful thing is this bulk to boundary propagator, which in momentum space has this form. So nu here is a spectral parameter. It's just delta minus d over 2. K here is the magnitude of the boundary momentum. H is a Hankel function of the second kind. This object n here is a normalization that I won't specify for now just to make life simple. And then the simplest object you can compute with these bulk to boundary propagators are to take n of them, right? So n of them ending at n points on the boundary and then meeting at a single point in the bulk, and then integrating over the conformal time associated with that point. And that's known as a contact diagram. Okay, and then the other thing you need are bulk to bulk propagators. I won't write them out explicitly. Really, the main thing we need to use for this talk are that they obey these simple equations of motion. Okay, where eta and eta bar are two different conformal times. Okay. Good. So now I think we have everything to answer the first important question, which is how do we lift the scattering equations that I showed you before to de Sitter momentum space? And it turns out that the answer is very simple. Whenever you see an inner product of momenta, of external momenta, I replace it with an inner product of boundary conformal generators. where this index A and B refer to external particles. Okay, and this inner product of conformal generators, this can be written in this simple way. So it's just constructed out of the momentums and conformal boosts for particles A and B, and the rotations and the dilatations. And the other rule is that whenever I see a momentum conserving delta function in D+1 dimensions, I have to replace it with a momentum conserving delta function along the boundary and a contact diagram. Okay, and now we're good to go, almost. And I should say that this form of the scattering equations was inspired actually by some scattering equations that were first written down in ADS embedding coordinates by these groups of people. But as we'll see, at least for the applications I'm interested in, the momentum space approach is much more useful. So let me explain why. So one way to see that why it's very useful is that it makes the flat space limit manifest. So with a little bit of algebra, you can show that if I act on both the boundary propagators for legs A and B, with conformal generators A and B, there's this very useful identity, which is that it can be written in this way, okay? And then you can just read off the flat space limit very easily from this. Now remember, there's a boundary at eta equals 0, all right? So the way to see the flat space limit intuitively is just to go very, very deep into the bulk. Go to eta goes to minus infinity, because then essentially you're pushing the boundary off to infinity. You don't see it anymore, and you're essentially like in flat space, okay? So in this limit that eta goes to minus infinity, the Bessel, the bulk to boundary propagators have this asymptotic form. And so we see that when we act on it with an eta derivative, at leading order, when eta goes to minus infinity, the dominant contribution comes from acting just on the exponential. Yeah? So essentially we can just treat it like a plane wave in this limit. And so when we act on the exponential with d by d eta, that brings down a k, the magnitude of the momentum. And you can see that this goes to ka times kb with a minus sign plus ka dot kb. And that's just the inner product of 2 4 momenta, right? That you would get in flat space. And so whenever you see operators like this that will appear in the curved space scattering equations, you can see very easily that in the flat space limit, they're going to reduce to the standard flat space scattering equation. That's not easy to see in position 3, for example. Okay, good. So after we realized this, we were able to write down a formula for any number of legs for the tree level wave function of massive phi to the 4 theory in de Sitter space, which can be thought of as a toy model for inflation. So if you like, this is sort of, at some rough level, you can think of this as an analog of the Park-Taylor formula in de Sitter space, in the sense that it describes any number of legs. It's not for spinning particles, it's not for gluons, of course. That's much more difficult at this point. But nevertheless, it takes a very simple and interesting form. So I won't have time to go into all the details, so let me just point out the key properties. So first of all, you see this integral over worldsheet coordinates support on scattering equations, just like in flat space, except that now the scattering equations are operators, right? They're constructed from these boundary conformal generators. So it's for that reason much more subtle than in flat space, because they're no longer commuting objects. The other thing is that we introduced this mass deformation mu, which allows us to take these scalars to have any mass. And otherwise, though, it's a very, at least formally, it's a very similar idea. And then we have to specify the integrand. And the integrand can also be written in terms of very simple building blocks, which I'll describe a little bit later in the talk. But for now, let me just point out this factor here, sigma 1, 2, sigma 2, 3 up to sigma n1. This is essentially the Park-Taylor denominator. This is the same structure that appeared in the Park-Taylor formula, if you use your imagination a little bit, that I showed at the very beginning of the talk. Then there's this Pfaffian, that's the square root of the determinant, of a certain operatorial matrix. And the elements of this matrix are basically the scattering equations, the objects that appear in the scattering equations. Ooh. Sorry. There is one thing, though, that if I just take the Pfaffian of this matrix, naively it'll vanish. So in order to make it well defined, I have to remove 2 rows and 2 columns. Okay, that's what's meant by this prime. But which 2 rows and columns I remove don't matter. And then finally, there's this interesting thing, which is a sum over what are called connected perfect matchings. I'll go into that a little bit later. The point is that this is an endpoint formula. It can be constructed from very simple building blocks. And what's quite nice is that in principle, you could worry about it being ill-defined. In other words, the scattering equations are constructed from these operators. The integrand is constructed from these differential operators. You may worry that if I shuffle them around, I'll get different answers. But it turns out that at least up to 8 points, it's not the case. I don't have a proof of this in general, but we checked that up to 8 points, we can reproduce Witten diagrams using this formula. And I'll tell you how momentarily. But as I said, it's much more subtle than in the flat space case because these are operators. So you have to be careful about that. For example, in flat space, one way to evaluate this integral would actually be to literally solve the scattering equations for these sigmas. And so this is a way of computing amplitudes that makes no reference to the standard Feynman diagram. You can recast this as a polynomial of degree n-3 in the sigmas, and then solve for its n-3 factorial, n-3 factorial, and then solve for its n-3 factorial roots. And then you just evaluate this integrand on each of these n-3 factorial solutions. We can't do that in flat space yet because these are operators. So in practice, what we do is that we treat this thing here as a contour integral. And then we use some residue, and we basically evaluate it using residue theorems and then map it into Witten diagrams. So it's not quite at the level of understanding that people had in flat space, but at least in principle, this is a formula that makes sense.
This is clarification. Psi n are the coefficients in the perturbative expansion.
Yeah.
So these are the things that get the phi to the n terms in the perturbative expansion.
Yes, yes.
I see. And so it's the wave function itself that resembles the time thing, and we still have to integrate this thing.
Yeah.
Okay.
Yeah, that's right.
So, like this, I think you can also write this in terms of operators if you go instead from a translation invariant to a Lorentz invariant basis.
I missed the beginning of your sentence. So you can write what is operators?
In that case, you can also replace the momenta by operators.
Oh, this is true.
And does that help? Can you then, because in fact you already know the answer, so the statement with operators and then maybe operators.
Well, yes, I am familiar with this work of working I mean, you can recast flat space in this more complicated form. Exactly how to I mean, really what it boils down to is finding the spectrum. It's like a spectral problem, finding the spectrum of these operators. So if I know the eigenfunctions and their eigenvalues, then in principle I'm good. But I think in flat space I would guess that the operators you have to diagonalize are very different. But it's maybe a nice warm-up exercise to think about how it works. I guess the point is that in flat space there's just plane waves.
Right, but the thing with the different bases where you use wave functions that are invariant with Lorentz, these are called conformal wave functions.
Yes.
And when you go to that basis, you have to replace all the momenta by operators. And then when you're casted in this way, maybe you can translate all the statements that you know from the usual factor to the operator balance statements, and then maybe that helps to make progress.
Yes, maybe. It's a good point. Yeah, I am familiar. I am aware of these papers you're talking about, right? And in this conformal basis, it's interesting because it sort of mixes UV and IR, right?
Yeah.
So in principle, it's sensitive to the high energy limit, which is interesting, of course. Yeah, I don't know exactly how to connect that, but I think that could be a useful. That could be some kind of useful intermediate step. I think what I can say about this, at least, excuse me, is that on a computer I see no problem, right? I mean, the trouble is that these things are complicated looking differential operators to diagonalize, and I think people have looked at how to do it using integrability methods, but this stuff is incomprehensible to me, to be honest, and I'm not sure. They commute in the first place? I don't think that in the end people actually manage to do what you would like.
Do the DA.dB commutes or not?
Oh, the DA.dB in general, they don't. They don't.
But even the SA and AP don't.
SA?
Sorry?
Even SA.
Well, the SA actually do, believe it or not.
Okay.
The scattering equations do commute with each other, which is non-trivial to see.
On the locus where they vanish, or just
I'm going to say yes, but I have to remind myself. But yes, indeed, in practice, yes, I think it must be. I think yes, it's on yes, it's on the.
So your additional different you were saying that the other end is not obvious, that they commute everything.
In practice, yes. Yes, for this theory, everything does commute, believe it or not. On the on this locus, on the support of the scattering plates, everything does commute, but it's very non-obvious. Yes, yes, but to me it's not obvious. I don't know, I'm not sure how to prove it in general. This is just an observation we've made. And then later on in the talk, I'm going to talk about more general theories that involve derivative interactions. And in that case, they don't, I think, naively. So you have to invent some kind of prescription to make this integral well-defined. But at least for this night, at least for polynomial interactions, they commute. So number one, they commute. This is important. They commute on this locus, and it's also important that you're acting on a contact diagram. They commute on the action of a contact diagram. So if you like, so I see where you're going with this. You're saying they commute, so they can be simultaneously diagonalized, and somehow this contact diagram is a linear combination of this subspace where all these operators are commuting. So there's definitely some interesting mathematical structure here. I don't really understand it very well, but what I want to say is that, okay, this probably you can do a lot analytically, but if you just wanted to be, if you were impatient, what you could do is just do this numerically. Just take these differential operators, put them on some lattice, find their eigenfunctions and find their eigenvectors and then eigenvalues, and then just try to evaluate these things numerically. And then the drawback is that, of course, you wouldn't have analytical formulas, but in principle, you could then at least plot the results of these correlators, which is something interesting that I don't think anyone is trying to. Okay, so in practice, that's not what we do. So in practice, we actually map these things back to Witten diagrams for the purpose of just convincing ourselves that this formula is correct. And so let me give you an example of how we do that. At 4 points, it's quite simple because in phi to the 4th theory, it's just a contact diagram, 4-point contact diagram. So what you do is, for example, as I said, you have to remove 2 rows and columns from the A matrix. Let's suppose we do it for legs 1 and 4. You have to fix 3 legs. So let's, for example, choose legs 1, 2, and 4. And then what we're left with is an integral over the puncture for leg 3. And that's supported on the scattering equation for leg 3. After some algebra, you can simplify the integrand to this very simple form, where S3 hat is a rescaled version of the scattering equation for leg 3, so that I don't have poles, but rather these sigmas appear in the numerator. So basically, the scattering equations, what I did was I multiplied out by all the denominators, and then I got something with sigmas on the numerator. It's a slightly easier object to deal with. And then this contour, it encircles the location where S3 hat vanishes. But then what you notice is that there's another pole at sigma 2,3. So what I can do is just wrap the contour around the sphere to encircle sigma 2,3. And then this thing becomes very easy to evaluate. So I just compute the residue at sigma 2,3 is equal to 0. So when sigma 2,3 is equal to 0, this term dies. This term dies. And what I'm left with is alpha 2,3 times sigma 1,3, sigma 4,3. Now, alpha 2,3, remember, it's just some differential operator that very nicely cancels this alpha 2,3 that came from the Pfaffian that I was talking about. And so what I'm left with is just a 4-point contact diagram, which is not mind-blowing, but at least it gives you a flavor of how we were doing these calculations. And so let me just quickly tell you what happens at higher points. So at higher points, we have to sum over connected perfect matching. So what those are basically, you sort of draw points on the circumference of a circle corresponding to external legs, and you draw chords connecting them, and the connected perfect matchings are the ones where the chords intersect, basically. And there are 2 types. There's this 6-point vertex, if you like, and then there are these 2 3-point vertices. And then when you use the residue theorem, what you find is that this term vanishes, and what you're left with is something that looks like this. Okay, and this, of course, resembles very much a 6-point Witten diagram with 2 3-point interactions. Of course, that's not manifest because right now this is just a function of worldsheet coordinates. But again, after you do the global residue theorem, I'm not going to go into the details of this. What you end up with for this diagram is this very interesting expression, where I take the conformal generators for legs 3, 4, 5, I square them, and then I invert this object. And then I act with this inverted operator on the contact diagram. But that turns out to just be equivalent to inserting a bulk-to-bulk propagator between legs 3, 4, 5 and legs 3, 1, 2. And that's a consequence of this very, very nice identity here. Okay? So the point is that the insertion of bulk-to-bulk propagators can be written in terms of boundary conformal generators acting on a contact diagram. Okay, and this is how we build up all the tree level Witten diagrams in this way. And then the non-trivial statement is that this world-T formula nicely encodes that and doesn't appear to have any ambiguities coming from the naive non-commutativity of these differential operators. Very good. And then you can also go on to loops. I won't go into a lot of detail about this, but the idea was inspired by the scattering equations for loops in flat space. And the idea is to take an n+2 point wave function coefficient, if you want to describe one loop endpoint, and then deform two of the legs in some sense. And by deform, I mean take the spectral parameter to be unfixed. Okay? And then to integrate over that spectral parameter. Okay? And then it turns out that integrating over this parameter omega essentially pastes together the two bulk to boundary propagators, auxiliary ones, into a bulk to bulk propagator. And so that's how you construct a loop amplitude out of a tree level amplitude. This is in some sense the curved space analog of Feynman's tree field. Okay, and around the same time that we proposed this in momentum space, a similar structure was also found in position space.
But may I ask what do you check? Actually, you have this idea that might be the right answer, and then you check against within there.
Yes, that's right, yeah. So again, we just use these residue theorems to check, to basically recast it as a Witten diagram. But the idea is that in principle, if you understood these, the spectral problem very well, you could do these calculations in a way that makes no reference to Witten diagrams. You could just really phrase it in terms of, in some sense, solving these scattering equations and summing over their solutions like people did in flat space.
Is it a one-to-one map with Witten diagrams? If there's multiple diagrams contributing?
Yes. So this is an interesting point. I didn't go into this, what I meant by psi twiddle here. So in psi twiddle, what I have to do, I have to modify this sum over perfect matchings a little bit. There are two types of one loop diagrams, right? There are the one PI diagrams that I've depicted here, and there are also diagrams corresponding to a one loop correction to the external legs, and those need to be treated slightly differently. So, but the way to treat them is just to there's a simple way to identify the latter type from perfect matchings. So you can either remove the perfect matchings that give rise to these self-energy corrections, and that would give you like a 1pi loop diagram. Or if you want to include them, you have to multiply them by a factor of 1/2, I think. Something like that. So there's a little fudge factor you have to include in the sum over perfect matchings to get these Witten diagrams right.
So the Witten diagrams have a virtue, which is to make the analyticity manifest at least at tree level. Whereas if you solve these scattering equations, you get branch cuts everywhere, and then in some miracle that the branch cuts.
Yes, that's right. Absolutely right. Even in flat space, you can see this, right? Because in flat space, at 4 points is a linear equation that you need to solve. At 5 points is a quadratic equation, which will involve square roots, and yet in the end, somehow when you combine everything, you get a rational function, and then beyond 5 points, of course, it's indeed, yeah. So the solutions to scattering equations in general are not rational, and yet the final answer is.
So is it understood why the final answer? Is it manifest from the formalism or?
No. It's a good question.
There's some
Indeed. I'm sure there are papers that have been written on this. I don't know. At least I'm not sure that I understand it very well. Why this is happening. But people have thought about this. It's a good question, and then there should be presumably something even more sophisticated going on in curve background. It's a very good question. Good. So at this point, let me just talk about the next steps that one would like to do. For example, one thing would be to extend this to more general scalar theories by looking at more complicated integrands. Hopefully, extend it to more realistic theories by breaking loose and conformal symmetries in order to make contact with observations. The other thing one would like to do is extend this to spinning correlators, so in particular gluons and gravitons. And the reason, one of the reasons why this would be very interesting is because then it would perhaps provide a systematic formulation of the double copy and curved background, which is still unclear. And as we said earlier, it would actually be nice to be able to explicitly solve these scattering equations. We call them the cosmological scattering equations because we're working in de Sitter. That's what CSE means.
Is this new formulation efficient in computing observables?
Oh, efficiency, it depends whose hands it's in, right? I mean, for us, it's not, I would say probably no. No, not at this stage, but efficiency wasn't our real goal here. I think in principle, you know, if one developed the technology enough, it could be turned into an efficient tool. At this stage, though, it's too early to say. Yeah.
I don't think I understand your answer because I thought efficiency was the main goal. I mean, otherwise, why would not you?
Well, I mean, it depends on who you ask, right? It's a philosophical question. How you define interesting, right? You know, being able to compute things quickly is a useful thing to do. Getting theoretical insight into mathematical structure is another interesting thing to do. I think my personal interests are more towards the latter. But of course, these two things are not disconnected, right? I mean, usually something that's mathematically beautiful turns out to be useful. I think, given my current understanding of how to do these calculations, I'm not sure that it's a more efficient way than just writing down Feynman rules and doing these things. But down the line, I could expect that it could be turned into something more efficient. At this stage, I would say no, to be honest. But that's not my immediate goal. On the other hand, I do believe that down the line it could be turned into something more efficient.
Well, maybe one sticking point. So in the beginning, you mentioned that in flat space, the massless story somehow has wonderful structure. And consider the massless story with traditional methods is a horrible nightmare. And I don't know if in that case your formulas might give some insight or if the nightmare persists.
I would expect, well, you say the nightmare because of IR divergences?
Yeah, these longs that pop up all over the
Oh, yeah. Well, the thing is, we're not actually integrating these. Well, I mean,
yeah. If you do the loop expansion of the wave function, they may already appear there.
Yes, that's right. Yes, so I haven't actually evaluated these loop integrals. This is more of a formal thing at the level of the loop integrand. So what I'm doing here is I'm deriving the loop integrand. But
is it too formal to take the mass to zero limit of your formal formula?
Too formal? No. I mean, I think, you know, this mass parameter just sitting there. I don't. So yeah, you could just set it to be non-zero if you like to. Maybe
it would be nice to see
avoid these things.
Well, anyway, not for now, but whether these interest funkiness that appears in your language in some
no, that would be great. You know, if it gave some kind of nice practical tool for dealing with these difficulties. Yes, indeed, I agree with that.
Do you have any reason to believe that this formalism will persist once you break with symmetry? For example, if you look at Fourier cosmology.
Sorry, I missed the beginning of the sentence. The other reason.
Do you have any reasons to believe that the formalism will hold beyond maximally symmetric spaces?
Fourier,
for example. That's what you mean by breaking Gauss?
Yes, absolutely. That's right. Exactly.
So do you have any reasons to? I mean, is it a trivial next step or is it?
No. None of these steps I'm claiming are trivial. This is a wish list, if you like. Yes, I don't have any concrete statements about how to break the symmetry in a systematic way yet.
I guess there were some papers like Durham and others about putting background fields and those breaks.
Well, they're working in, I think, plane wave backgrounds.
Yes.
So that's a very different type of background indeed, and in that case, they do have some analog of the scattering equations as well. So yes, that would suggest that you don't have to restrict yourself to maximally symmetric spaces. That's true. Yes. So in fact, yeah. So when I say the next steps, this is not something I'm going to do tomorrow. I mean, this is what I mean is that this is something that I would like to do in general. And what I'm going to talk about in the remainder of this talk are just progress on the first point and the second to last point. I don't have much to say about the other points at this stage. Okay, so in order to motivate those 2 points, let me actually go back to flat space and tell you a little bit more about the double copy in flat space. So at 3 points, the double copy in flat space is trivial. You take a 3-point gluon amplitude, you square it, you get a 3-point graviton amplitude. To go beyond 3 points, it's a little bit more subtle. It's not just a squaring. It's something a little bit more interesting. And an important concept to extend this double copy to higher points is what's called color kinematics duality. And the way to see it is to, for example, take a 4-point gluon amplitude and then write it in this way where ST and U are the usual Mandelstam variables. And CS, CT, and CU are group theory factors, which add to 0 by the standard Jacobi identity. And then what it turns out is that it's possible to choose these kinematic factors, NS and T and NU, in such a way that they also obey some Jacobi identity. But this is not a standard one. This is in some kinematic space. And then once you've found these operators, the miracle is that you can obtain a graviton amplitude by replacing these color factors with another copy of the kinematic factors. So in other words, if I square the kinematic factor and add up these 3 terms, that gives me a graviton amplitude, which is quite amazing. Although this has been understood already for some time and extends to higher points and loops even. And it was initially discovered in the context of string theory, roughly speaking, from the KLT relations. But since then, it's pretty clear that this double copy really takes on a life of its own, in the sense that it's not restricted to theories that arise from some kind of limit of string theory. And as I said, it also extends to loop level, even in a field theory context. So in other words, you don't have to take into account this infinite tower of massive states that would arise in string theory. So I think the origin of the double copy is still not completely clear.
So it's kind of off-topic question. What is the sharp statement about double copy for loop? It's really.
What is the sharp statement? Yes. Well, it's a similar idea. So you have a loop integrand, and you write it in terms of these numerators, and you square the numerators, and it gives you the loop integrand for gravity amplitude starting from the gauge theory one. Is that sharp enough? Or?
Yeah, so I just meant and this works.
Yeah. It seems
all
there's okay. It depends on who you ask, but there's no proof of it. It's just been proved. It's just been shown to a very impressively high order.
It's proved by practice, right? You prove how the amplitude should behave by unitary method, and what you check when you put the PCJ on that, just by squaring, well, it solves everything.
Yeah, proof of practice. Yes, yes, indeed. I mean, but to all loops, I mean, there's some recent work, interesting work on where they claim to prove it using homotopy algebras and some technology that I don't fully understand.
But fail at some point. If you can't always choose the BCJ.
Does it? Okay. Is that true? I know that they encounter difficulties at like 5 loops or something.
But it failed by practice also because they don't know that, but at 5 loops, polynomial semi-control failed. The equivalent.
Okay. Yes. I think I'm familiar with that. I don't know if people say that's because the double copy doesn't work, or that it's just hard to find the PCJ numerators.
Well, there is an amount of things you can put if you allow them to be a rational function, and if you allow to have arbitrary eigendenominator at some point, it will always solve, but then it's not really useful in some sense.
Okay.
It fail in a reasonably decent context.
Okay, I see. Okay, well, yes. So I mean, the status of this is, I think it's fair to say it's not clear, right? But you know, it works up to 5 loops or something. So there's definitely some element of truth to this. Certainly, 5 loops is not something that I would ever, I envision myself ever attempting. But there are very powerful people out there who have attempted it, and they seem to be optimistic. So.
It's an equalization of gravity.
Yeah, because n equals 8 is very easy. Yeah. I think n equals 8, maybe even higher than 5 loops. But anyway, so indeed, this is at least for some very, very impressively high order, it seems to work straightforwardly. I mean, at least these people can do it straightforwardly. Well, I don't know if I could, but at least someone out there can do it straightforwardly. Okay. Very good. Okay. Oh yes, so now let me talk about the extension of this to ADS. So in ADS, it turns out that there is some analog of the double copy for 3-point correlators, which is in some sense inherited from the flat space limit. And then at 4 points, it turns out that there also is an analog of color kinematics duality. So we initially showed this in momentum space, and since then it's been analyzed from many other points of view. For example, in Mellon space and in position space. So it seems to be fairly robust there. And it's also been shown in something called the nonlinear sigma model. So if you take pions in ADS and you can rewrite the Witten diagrams in such a way that the numerators obey some Jacobi-like relation. But what doesn't seem to extend straightforwardly is this squaring operation. So if you find these numerators that obey the color kinematics duality and you naively square them, you get something that's not quite recognizable. And the way we discovered this is that I asked my students to do this. They spent a few months working on this, and it didn't work. And I thought to myself at that point, I said, okay, well, it's worth a shot. Let's move on and do other things. But then there was this beautiful paper by Xinan Zhu, who actually got it to work for very highly supersymmetric theories in ADS 5 times S5. So there's a lot of technology that he was using to simplify the problem. And at least in his language, this naive squaring does get it to work. So after that paper, I became very optimistic again that the double copy can indeed work in ADS once it's understood properly. Although I haven't quite, I haven't gotten there yet, but my expectation is in the next year or two, we may understand how to actually do it systematically. And that's kind of the motivation for the rest of the talk. Because what we're going to do, what I'm going to talk about is how the double copy works, not for gluons and gravitons, but for certain scalar theories. Okay, and this is a lot easier to work with because you don't have to deal with these tensor structures. And the idea is that the scattering equations should give you some interesting insight into how to think about the double copy. So coming back to this efficiency question. I think down the line, it could also provide you a more efficient calculational technique, but the other nice thing about the scattering equations is that it gives you it provides a useful way to think about these relationships between field theories that are very difficult to see using other methods. And so the scalar theories that I'm going to talk about are the nonlinear sigma model, the scalar Dirac-Born-Infeld theory, and this thing called the special Galilean. And how am I doing on time, by the way? I don't see a clock.
5, 10 minutes.
Oh, wow, okay.
10 minutes, we can say 10.
10 minutes, okay. All right, well, I'll do my best. I'm actually only about a little over halfway through, but I'll do my best.
We have 15 minutes budgeted for questions, so you can kind of...
Oh, good, so maybe if someone asks me to continue, I could continue. So at first sight, this seemed like a very random set of theories, right? Certainly before I saw the CHY papers, I had no idea what a special Galilean was. But it turns out that these are very, very interesting from the point of view of the CHY formula, because in flat space, they can be described, their integrands that I talk about have a very, very simple structure built out of these Park-Taylor factors that I showed you before, these Pfaffians, where I take this A matrix, and then I remove 2 rows and columns, I compute this Pfaffian, and another object, another Pfaffian of this X matrix. And where this comes from, roughly speaking, is from dimensional reduction of Yang-Mills, believe it or not. So in the CHY formula for Yang-Mills theory, you would have an inner product of 2 polarization vectors here, right? And then when you do dimensional reduction, what you do is you imagine these polarization vectors as living in some internal space orthogonal to the space of momenta, and then their inner products just become numbers. So that's roughly speaking where this X matrix comes from. And the reason why I'm telling you this is because the CHY formulation makes the double copy manifest. What's quite nice is that I can obtain the DBI integrand from the special Galilean and special Galilean integrand from nonlinear sigma model by these very simple operations. So I just replace the Park-Taylor factor with this thing, and that gives me DBI. And if I replace the Park-Taylor factor with Pfaffian of A squared, that gives me the Galilean. And I won't have time to go into details of this, but what these simple replacement rules encode are the double copy, which tell us that DBI is basically comes from taking nonlinear sigma model and multiplying it by Yang-Mills and dimensional reducing. And the special Galilean comes from squaring the nonlinear sigma model. And before this, as I said before, I think prior to the CHY formula, no one had any idea that such relations existed. And there are many other examples as well.
This is the nonlinear sigma model for what group?
SUN.
NEN.
Yeah.
That you need in the end because you replace the cutoff factor.
Yeah.
Okay. I'm still learning how to get this thing to go in the direction I want. Okay, very good. So what I'm going to talk about next is how to lift these things to curved background, in particular DS. Okay, and when you go to curved background, there are immediately many new complications that arise. For example, you get new types of interaction vertices proportional to the curvature, right? Which vanish in the flat space limit because obviously the curvature vanishes in the flat space limit. So you have to take into account these possible curvature corrections. And so I'm going to restrict myself to 4 points for now. And at 4 points, in the nonlinear sigma model, it's possible to add this phi to the fourth interaction, which just corresponds to a curvature correction. So just to be clear, where that phi comes from, what I'm doing is I'm taking this matrix, it's an element of SUN, and then I write it in this way, and then I can expand the action in phi. So phi is in the adjoint rep of SUN. Okay, so I get an infinite series of terms. Okay, so then if I truncate to 4 terms, I can add this curvature correction. And then for GDI and special Galilean, at 4 points, remember the special Galilean, it has a 6th derivative interaction, which is here. This is the naive uplift of that 6th derivative interaction. But then Polchinski and Penedonis and collaborators showed that up to integration by parts and free equations of motion, the most general thing I could write down at 4 points up to 6 derivatives has this form. So it has a 6th derivative interaction and a 4 derivative interaction, a contact interaction. And these 2 terms would be thought of as curvature corrections in that case, right? Then to lift dBi to ds, I would set this coefficient a to 0, and then this would be the naive uplift of dBi, but then there would be a single curvature correction. And right now I'm going to leave these coefficients a, b, and c unfixed. Okay, there's this ambiguity, if you like, in lifting to ds, which is that you can get these curvature corrections. And in order to specify their coefficients, you need to supply some additional data beyond the flat space limit. Soft limits, hidden symmetries, something along those lines. Okay, this is unfortunate that I labeled this coefficient a. It has nothing to do with the A matrix I wrote before. Hopefully that's clear from the context. Very good. And so then using the Witten diagram approach, it turns out that the 4-point wave function coefficient in the nonlinear sigma model takes this very simple form in terms of this generalized Mandelstam variable u hat. It's this differential operator here, constructed from the boundary conformal generators. And then from that 6th derivative effective action, I can write this 4-point correlator in terms of s hat t hat cubed, t hat cubed, u hat cubed, and then another thing involving s hat squared, t hat squared, u hat squared. This is coming from the 6th derivative part, the 4 derivative part, although the 6th derivative part actually mixes into the 4 derivative part. So you'll notice this a here, coefficient a appearing in 2 places. And then this is coming from the contact interaction. And what I'm going to describe to you now is how to reproduce this structure using the scattering equation. Okay. In other words, what is the integrand that I can write down for this world sheet integral that reproduces this simple structure? And it turns out that it can be written in terms of some simple building blocks. So these building blocks include the naive uplift of the integrand for the nonlinear sigma model and the dBi theory and the special Galilean theory. But I also need 2 new building blocks involving what I call Pfaffian of x connected. So at 4 points, the Pfaffian of x, it can be written as a sum of 3 terms. And you can visualize them as perfect matchings. And what I'm doing is I'm keeping the term that corresponds to the connected perfect matching. So this is actually what we saw earlier in the context of 5 and the 4 theory. So in other words, I'm keeping the perfect matching where the 2 chords intersect. For example, 1 over sigma 1, 2, sigma 3, 4, that involves a chord between 1 and 2 and 3 and 4. These are 2 disconnected chords. Okay. Good. And since time is short, I'm going to just keep moving. I'm not going to go into the details of choosing Pfaffians and so on. If you like, I can describe that later. And then it turns out that at 4 points, these Witten diagrams that I wrote down for you before, which were expressed in terms of these boundary differential operators, can be derived from these simple building blocks. Okay. So the key point here is that these coefficients A, B, C that appear in the world sheet integrand are unfixed. I'm not specifying what they are, okay? In the same way that I didn't specify the coefficients in the effective action, but I can match the results of these world sheet integrals to the Witten diagrams via this identification of the coefficients that appear in the effective action with the coefficients in these integrands. And the other key point is that this integrand for dBi and special Galilean in ds can be obtained from this one for nonlinear sigma model in ds via this replacement rule, which is some curved space analog of the replacement rules that I showed you in flat space in an earlier slide. But you can see that it's a little bit more complicated now because you have these new types of terms appearing involving phi of x connected, which encode mass deformations. And also, for example, in the special Galilean theory in flat space, B would be set to 0 because that's like a curvature correction, but in DS, in general, you have these additional terms that can arise. So in some sense, the double copy can be generalized at least at 4 points, but it gets deformed by masses and curvature. Okay, since time is short, I won't go into much more detail beyond that. All right, I have 2 slides left, if that's okay. Right, so the next thing that I want to talk about are soft limits. And these are important for a number of reasons. They have practical importance because it turns out that inflation, the time dependence of the inflaton, it breaks these conformal symmetries. But nevertheless, 3-point inflationary correlators can actually be derived from de Sitter 4-point correlators by giving one of the legs a small mass proportional to the slow roll parameter, and then taking the leg soft, that leg to go soft. So it's understanding soft limits of these 4-point functions is of great practical importance, but they also turn out to have some interesting mathematical structure, it turns out. So in particular, what we find is the soft limits can also be written in terms of boundary conformal generators acting on contact diagrams. So just to give you an idea, let me focus on the case of a conformally coupled scalar that corresponds to the scaling dimension delta is equal to 2 in DS4. And then when we take the soft limit of these building blocks that appeared in the Witten diagram here, so in other words, I'm talking about these building blocks here, this, and this, we get some very simple and interesting looking expressions. For example, if I take the soft limit of a 4-point contact diagram, I get this 3-point contact diagram, but it actually involves a time-dependent interaction. So this C3 eta, it involves 3 bulk to boundary propagators, but then there's this additional factor of eta in the integrand. So it's somehow like a time-dependent interaction. But then the point is that this 3-point contact interaction appears in the soft limits of all these more complicated building blocks. So, and then in the end, I just act on it with some simple combinations of conformal generators. And I should emphasize that this is actually very non-trivial, because if you actually evaluate these correlators, you do the conformal time integrals, you get very lengthy expressions. Right? And when you take the soft limit, the expressions are much simpler, but they're also fairly lengthy. So the fact that they can be related in this very simple way by acting with boundary conformal generators is actually quite non-trivial. Okay.
These literally the dilatation operator acting on each leg.
Yes, D3 is the dilatation for leg 3, for example. Yeah. And the other nice thing is that since an arbitrary 4-point correlator is constructed from these building blocks, you can choose the coefficients in such a way that there are cancellations between them. For example, you see this object here, which is quadratic in the dilatation operator, and this object here, which is quadratic. So if I tune the coefficients appropriately, I can get cancellations. So for example, it's possible to choose, if I chose the coefficients uppercase A, B, and C, in that effective action I showed you earlier, to take these particular values, I find that the soft limit of this 4-point function, 4-point wave function coefficient, takes this super duper simple form. Okay, and at least in flat space, our experience is that having simple soft limits usually indicates the presence of some kind of hidden symmetry. And so you may ask if this effective action has such a symmetry, or you know, what is this simple soft limit a consequence of? And I should say that actually Lagrangians for the DBI and special Galilean theories were recently, in DS4 were recently proposed by these people. And so it'll be interesting to see, I think, if their correlators, well, to compute their correlators in this language of boundary differential operators acting on contact diagrams, and to compute their soft limits and to see if they have any form of simplicity. Or at least to understand how these hidden symmetries are encoded in the soft limits. And the reason why is because then you could perhaps promote this to some kind of a principle for fixing the coefficients, these free coefficients in the generalized double copy. And the basic philosophy here would be to be able to reconstruct this theory just purely by imposing some very reasonable physical constraints on actual observables without ever making reference to the underlying Lagrangians like people would do using amplitudes in flat space. So that would be another interesting direction for the future. And since I'm out of time, I'm going to stop now. Thanks.
The questions from the Rebel Zoom.
So in analogy to flat space, those symmetries would be some BS version of large big symmetries or BMS flat symmetries?
Well, okay. So what you're talking about, these BMS-like symmetries, they appear in the context of Yang-Mills and gravity. For these scalar theories, they're shift symmetries. So they're basically coming from the isometries of flat space. And in the case of DS, there's some analog of these shift symmetries that these people use. How they're connected to these asymptotic symmetries, I'm not completely sure, but they're at least for it's a good question. I think at first sight they look different to me. These are just shift symmetries, not necessarily large gauge transformations that I think you're referring to. Yeah.
But so if you look at this for string correlators and you find some similar structure, then this might be the nice expectation. But in flat space, you also know that we can recast these as symmetries in some periodic boundary theory, where these are generators in the global conformal or some extensions that include the BMS superconfiguration symmetry. Is there an expectation here too that there's some purely boundary interpretation of these symmetries? So some 3D generators.
It's a good question. I don't really have. Okay, so there are lots of questions in there. Let me. So the first. Let me try to rephrase it. Maybe is this an accurate way to rephrase one part of the question? So the first question thing is there an analog of BMS in curved background?
I guess this hasn't been done for the student.
Not by me, at least. I'm not aware of it. I
people try to compute asymptotic symmetries in this.
Yeah. No, I mean, I think it's an interesting question. I haven't gotten there yet, but it's a very interesting question. And then the other thing you asked about was what is the interpretation of these symmetries from some kind of boundary perspective? Right. Well, I mean, all I can say is that we've managed to write these soft limits in terms of boundary differential operators acting on a contact diagram. So which is, obviously, if you're interested in the boundary interpretation of soft limits, that's the first thing to do. Beyond that, I don't know whether you can derive this from some kind of word identity of a CFT, the way people do in the celestial amplitude program. It's a very interesting question. At this stage, all we have are these formulas, which I think are a surprise to us. They're so simple. And I should say that for the case of minimally coupled scalars, they have a different form. They're not just written in terms of dilatations. They're written in terms of dilatations and conformal boosts. But nevertheless, it's still possible always to write these things in terms of boundary differential operators acting on contact diagrams. And you may say, okay, well, don't you expect that since your original correlators were written in terms of boundary differential operators acting on contact diagrams? Well, no, not quite, because these new types of contact interactions that appear are in a different theory. First of all, they don't vanish at odd points, whereas in phi to the fourth theory, the correlators vanish at odd points. Second of all, they involve time-dependent interactions, for example, in the case of the conformally coupled scalar. So there's some kind of new theory appearing, if you like, in these soft limits. So I think the fact that can be written in this way is not a trivial thing, and I think having some deeper understanding of the origin, maybe from a origin of the structure, either from some boundary point of view or some other point of view, would be very useful. I think that's an excellent question. Yeah. Oh, well, okay. Maybe
Go ahead.
I just wanted you to have taken a flat space limit of this structure here. And
very good. Flat space limit does not commute with soft limit, actually, in ADS. So this is an interesting question. These things seem to be, I don't know how to connect them to the naive flat space limit. In the flat space limit, of nonlinear sigma model and DBI and special Galilean, famously, they have what are called enhanced soft limits in flat space. So they vanish, and they vanish to some high order in the soft momentum. So it starts kicking in at some high order. And this is a consequence of these hidden symmetries. Now in DS or ADS, that's not the case. And the reason is because the soft limit, the flat space limit probes short distances. It's going to a limit where energy becomes conserved and the curvature sort of goes away because you're zooming in so close to some spot in ADS. The soft limit is the opposite regime. The soft limit sees very much the curvature. So when you go to energy goes to zero, you're probing very large distances and you can feel the curvature. So the soft limit actually seems to be physically going in the opposite direction than the soft limit. And so these soft limits naively have a very different character than the ones in flat space. But yeah, this is something we were thinking about for a while.
You also have a nice structure that you have this factorization into a lower point amplitude and then some operators acting on.
Yep, exactly, yes. So there's, I think, some analog of these soft fear of these enhanced soft limits or whatever. I mean, I think the point is that in flat space, you have these theories have very, very simple soft limits, and the reason for that is because they have some hidden symmetries. In curved background, the soft limits are very different, but I would still expect that somehow these hidden symmetries should be encoded in these soft limits, although I don't know how at the moment. So that would be an interesting question to answer. Right now, all we have are these formulas, and now it's time to take a step back and digest them and try to understand what their significance is or what their origin is. Offline, okay, good.
Yeah. When you work on this, this is a nonlinear sigma model action. So you have a mass, and you also have the radius of the sitter.
Mm.
You can make a dimensionless combination and
yes,
insert all kinds of functions of this thing.
That's right.
So why do you exclude this possibility?
So what possible? Well, okay, exclude. So in practice, the way I think about this is that I measure the mass in units of the inverse ADS or DS radius. So I think of it as being some kind of dimensionless parameter multiplied by 1 over, well, m squared is some dimensionless parameter multiplied by 1 over r squared, where r is the DS radius, or if you like the Hubble constant. And then in the flat space limit, if you keep this dimensionless parameter fixed, everything just becomes massless. You could consider another limit where you take the DS radius to infinity and this dimensional parameter to infinity, and then what we would land on are mass deformed scattering equations in the flat space. And those were actually first discovered by Dolan and Goddard. Okay.
Okay, so if no questions, then let's thank Operator.
Thank you.